Welcome to our electromagnetic field lecture series. In this lecture 20, we are going to discuss on displacement current. The objective of this lecture is to first investigate the phenomena of displacement current due to time-varying electric field. Secondly, to investigate on changes of Maxwell's equation for time-varying field due to the concept of displacement current. And third, to learn about the concept of lossy dielectric and how it is used to classify material. Let's recall our lecture 12 in which we were discussing on capacitance. For a parallel plate capacitor connected to a circuit, current flow would positively charge one plate of the capacitor structure and the other capacitor structure plate would be negatively charged. In between the plates is dielectric material. In the absence of conductor, there will be no conduction current flowing within this capacitor structure. So how does current flow from one side of this capacitor to the other side of this capacitor? In this lecture, we would fine-tune our understanding of how a capacitor operates. The phenomena to be discussed is using the concept of displacement current. In our lecture 16, we have presented the Maxwell equations for static field. We are going to focus now on these equations where we had applied Stokes' theorem to Ampere's circuital law. From earlier lecture 9, we have presented the continuity current equation, in which del dot J is equivalent to negative d rho v over dt. Rho v can also be equal to del dot d. Hence, the continuity current equation can be said is associated to a case of time-varying d fields and subsequently time-varying E fields. Applying this continuity current equation to the point form of this Maxwell equation, we can get this mathematical relation. Hence, we can also relate that del dot del cross H is equivalent to negative d over dt of rho v. That is also equivalent to del dot d. Thus, this is the relation of magnetic field intensity as well as electric field density in the case of time-varying electric field. However, there is one mathematical law that states that the divergence of the curl of any vector field is identically zero. Therefore, to ensure that our mathematical relation here conform or abide by this law, we need to add a mathematical term on the right hand side of this mathematical relation such that this term here would be negated and the right hand side would become zero. The mathematical term to be added is d over dt of del dot d. With this, the original relation that was shown earlier would be modified to become del dot curl of h is equivalent to del dot d over dt of d plus del dot j. Del dot of vectors can be said to be divergence operations. Removing divergence operation on the left hand side and the right hand side of this mathematical relation, we would get the curl of h is equivalent to j plus d over dt of d. We are now going to associate the concepts presented earlier to the supposedly current flow within the dielectric material region of a parallel plate capacitor. To do so, we are going to review back the Ampere's circuital law. Supposedly, there's current flow on the conductors at these two ends of the capacitor. If we are to create a closed loop, we can determine magnetic field intensity using the Ampere's circuital law. However, if we have the closed loop within this dielectric material region, we cannot apply the Ampere's circuital law directly, given that there's no conductor as well as there's an absence of current element. Nevertheless, within this region, as current flow to this plate of the parallel plate capacitor, positive charge that accumulate would radiate electric field. And as electric field is being radiated, the charge here would be depleted but would be immediately replaced by incoming charges from the current flow. We have also presented in lecture 9 that an applied electric field would result in current density. So what sort of current density can be included in this region? The current density to be included in this region is the current density that is allowing current flow to move from this position to this position. Or we can say current density that allow the displacement of current flow from here to here. We shall call this displacement current density. Displacement current density is not the case of current as a result of charge movement, but rather due to time-varying field. We can now introduce the displacement current density in our point form Maxwell equation. From earlier derived mathematical relation, this mathematical term here can now be associated with the displacement current density. We'll therefore conclude that the current flow inside dielectric material is due to displacement current density. Equation 1 here is the Maxwell modified equation for time-varying field. From previous slides, we would now demonstrate or present the resulting time-varying field Maxwell equation. Based on lecture 9, the curl of E field is equated to the negative d over dt of magnetic flux density. From previous displacement current derivation, we would describe that the curl of H is equivalent to J plus d over dt of electric flux density, or D. For a parallel plate capacitor that is being filled with a perfect dielectric material in which conducting current density, or J, is equal to 0 and sigma is equal to 0, the cross of H can now be equated to only d over dt of D, or can be equated with the displacement current density. In many practical cases, we cannot see J is equated to 0 or sigma is equated to 0, given that the material within the capacitor are lossy dielectric materials. Let's, however, consider a case of a lossless dielectric material. We can therefore write equation 1 above based on this relation, in which curl of H is equated to d over dt of D. Another way of writing d over dt of a vector is writing it as j omega of that particular vector. From that supposedly approach of writing, we can now describe that the curl of H is equivalent to j omega d, or epsilon E. For a lossy dielectric material, in which the curl of H can be written as equivalent to j plus j omega d, we can determine that this equation can also be written as j is equivalent to sigma E, and j omega d is equivalent to j omega epsilon prime E. Epsilon prime is the permittivity of the dielectric material, the lossy dielectric material. Hence, given that these two terms has E, we can factor it out such that equation 3 is derived. To investigate the relation of dielectric permittivity in lossless and lossy dielectric, we shall equate equation 2 and equation 3 previously shown. We can therefore write that j omega epsilon is equivalent to sigma plus j omega epsilon prime. Dividing all the mathematical terms with j omega, we would get this relation that can be also be written as this mathematical expression. If we are to factor out the lossy dielectric permittivity, we would get this mathematical relation, and this mathematical terms here, which is sigma divided by omega epsilon prime, which is the lossy dielectric permittivity, is equivalent to loss tangent. The loss tangent would describe the relation between conducting current as well as displacement current. For a lossless dielectric material, loss tangent would be equivalent to 0. The loss tangent concept can be used to classify material. A good conductor would have a very high loss tangent value. On the other hand, a bad conductor would have a small loss tangent value. Material with small conductivity can be expected to become a good conductor if frequency used is very small, in order to increase the loss tangent. For a lossless dielectric in a parallel plate capacitor, we would model the current within the dielectric material as being only displacement current. On the other hand, for a lossy dielectric material inside a parallel plate capacitor where there exists a value of sigma, certain amount or very small amount of current, conduction current, would flow. Thus, we would model it as having displacement current as well as conduction current that would be considered as a leakage current. In our next lecture, we are going to discuss on propagation of plane wave in free space.